this keeps up. That may be how the people here may have to watch this is on the recorded part. Let's see what I can do. All right. So we have methylamine. You guys remember what amines are? Basically, an amine is an NH3, but one of the H's has been replaced with some type of carbon chain, right? In this case, it's methylamine. So that carbon chain is one carbon only. And that carbon is connected to 3 hydrogens. We're going to add that to water. So let us ask, actually, let's see if it asks these questions. Doesn't look like it. So if we look at this, what is methylamine here? What has it done? If we take a look from here to here, what has it done? Gained a hydrogen. So this is a proton acceptor. So what kind of compound is that then?
Base.
Base. This was a proton donor. So this is an acid. What does that make this guy? Conjugate acid. And this guy? Conjugate base. So it says methylamine is a weak base. There we go. That reacts according to the equation above. The value of ionization, the ionization constant Kb is 5.25 times 10 to the negative 4th. So right there, the fact that this is not greater than 1 tells us that it is a weak base. Methylamine forms salts such as methylammonium nitrate. And there we go. There's the methylammonium nitrate. And if you take a look at that, then we have the +1 charge and the -1 charge. Question?
I don't know if it's just me, but I can't see what you're doing on the Zoom.
Yeah, neither can I. I just left and rejoined, and it's still nothing.
It's, yeah, there we go. This is why I use the other computer. Like I said, we're having some technical difficulty. How's that?
Yeah, that's better. Thank
You back? Okay, good. So there we have the proton acceptor, the proton donor, and then we have basically this this cation forming, which could then form up and make something such as methylammonium nitrate, which basically is just an ionic compound. This is calculate the hydroxide ion concentration of a 0.225 molar aqueous solution of methylamine. So if we have our formula here, CH3, NH2 plus H2O, CH3, NH3 plus OH negative. So what we're going to look at here is we have 0.225 molar aqueous solution. And they want us to calculate the hydroxide ion concentration. So we are starting this solution with this many of this guy. And that will be our initial. And we don't care about H2O. Why don't we care about H2O? It's a liquid. And we have, at the start of all of this, we have 0 of this and 0 of this. Since we have 0 of this, the equation has to go in which direction? Forward. So that means we will lose 1x of this. And we don't care about this. We will gain 1x of this and 1x of this. And again, those 1x's are just because of the coefficients up there. So what this becomes, that is the change. At equilibrium, we will have 0.225 minus x. We will have x and we will have x. Questions there? Now again, normally when we do this, we have K sub BQ. Since this is a base, we've identified this as a base. They've actually specialized the equilibrium constant to make it a base equilibrium constant. So we have Kb equals products over reactants And those brackets refer to concentration. So we will take a look and then we'll set all of this equal to 5.25 times 10 to the negative fourth. And that is equal to, at the top, x times x, which is x squared, and at the bottom, 0.225 minus x. Again, with this, we could put this into the solver equation on our calculator. If we have our calculators available, that's perfectly fine. Or we can ignore this little minus x right here, because our case of B is so small. The amount of that we actually lose of this is not going to be much compared to that amount. So, and we just ignore that. We have 5.25 times 10 to the negative fourth times 0.225, and then we square root that answer. I got 0.0. Actually 0.01089. I'm sorry, 0.0109. That is X, so that is our concentration of hydroxide ion. Cool. If we were asked to find the pH here, what would we do? Negative log of that. And we get 1.96. And we need to do what to that? We subtract that from 14. And we get 12.03, which makes sense for a weak acid, or I'm sorry, a weak base to have a pH of 12.04 in this case. Questions there? All right. So then they say calculate the pH of a solution made by adding 0.01 moles of solid methyl ammonium nitrate to 120 milliliters of a 0.225 molar solution of methylamine. Assume no volume change occurs. No volume changing occurring here is kind of big, because if there was a volume change, then these concentrations would be different, and we would actually have to go to moles instead of dealing with concentration for this. So with this, we can reset this up. So this time we have still the 0.225. But as we can see here, we have 0.010 mole of solid methyl ammonium nitrate. So we actually have some of this. Why aren't we concerned about the nitrate part of this? Is the nitrate part of this reaction? What does that make the nitrate then? What do we call that whenever something is present, but it does not partake?
Is it a spectator ion?
Spectator ion, good. Home team and here team both got it, good. So I'm going to go ahead and 0.0100. And I need to find the concentration of this right here. So I need to divide that by the volume, which is 120 milliliters. 0.01 divided by 0.120. And we get 0.0833. So again, we don't care about the H2O. We get 0.0833. We still have zero of this hydroxide. So which way is our reaction? Moving forward or reverse? Forward to make that hydroxide. So again, we are going to have minus X here. We're going to have plus X here and plus X here. So this will again be, is their change, Here's our equilibrium. 0.225 minus x, 0.0833 plus x, and x. Questions there? So again, this is the same reaction, and the temperature has not changed. So our KB is equal, it's the same as it was before. So we'll go ahead and plug that in. KB equals the same as up here. It's just that now we have some of this stuff. So we need to plug that in 0.0833 plus x times x, and then 0.225 minus x. Which of these can we ignore? Minus x and the plus x. Again, we can check that at the end if you're nervous about that. But the AP exam said they're not going to have you do the quadratic equation. So we can ignore those. I mean, for these problems, this is an AP problem. So, I mean, we should be able to in our mind. So we take a look again, we have that 5.25 times 10, what? Times 10 to the negative fourth. We're going to multiply that by 0.225, and then we're going to divide that by 0.0833. We get 0.00142. Right? That's a 0.6% difference, so that's definitely less than a 5%. So x equals this. So what is this exactly? Well, that is equal to our hydroxide ion concentration. And just as a problem before, if we wanted to find the pH of this, does it ask? It does ask. It says calculate the pH of this. So this is our hydroxide ion concentration. And remember that, what's the other way besides what he said, negative log and then subtract it from 14? What else could we do? Nobody? So if this is the hydrogen ion concentrate, hydroxide ion concentration, remember the hydrogen ion concentration times the hydroxide ion concentration has to equal 1 times 10 to the what? Negative 14. That is what we call the KW, right? So we could take 1 times 10 to the negative 14th and divide it by this, and that would give us our hydrogen ion concentration. And then we could take the negative log of this, and that would give us our pH. I missed an O. I missed an O up here. That's going to be wrong then. Let's do that. 1 times 10 to the negative 14th divided by 0.001418. There we go. And then we take the negative log of this. We get 11.15. There we go. Mathematically speaking, you guys hopefully I can just tell you. So if we take the negative log of something, that basically, for example, if we have the negative log of 1 times, this is like a little side, this isn't part of this problem, 1 times 10 to the negative 12. So if we take the negative log of that, that would be 12. So the pH would be 12 if this were the hydrogen ion concentration, right? So if there is a number here, then it will be less than 12. Because like 1 times 10 to the negative 13 would be, the negative log of that would be 13, right? So if we take a look, if we have a number here, it's going to be less than. If it's a bigger number like 10 or something like that, obviously it's going to be greater than 12. So if you have a number here, it would be between 11 and 12, which basically then it'll allow you to quickly do, like, for example, multiple choice problems. For example, let's say if you don't have your calculator, which you're not supposed to during the multiple choice portion of the p-test, then they may give you something and they say, okay, now you have to figure out what the pH is. Now, if you know this, that's kind of what that means, the power of hydrogen. This is that power. It is the negative log of that, so it would be 12. If there's a number next to that instead of 1, then it's going to be less than 12. So it'd be 11 point something. That's just to help you guys a little bit on multiple choice stuff if you have trouble with it. All right, Gibbs free energy. We need to bring back that concept of entropy, which basically is disorder. So the first law of thermodynamics is that energy cannot be created or destroyed. It can only be, transferred. Second law of thermodynamics basically states that the disorder in the universe increases. We know this if you have a junk drawer at home. We know this if you look at your room. Somehow it becomes messier and messier. You actually have to physically put energy into it in order to organize it, right? Same thing happens to the universe. So yeah, you can just be like, it's entropy, Mom. I can't help it. Mom's like, clean the room. It's entropy, Mom. I can't help it. This is the way the whole universe works. And basically, you can't break even. You have to reorganize that stuff. You have to put energy into that and reorganize it. I'll let you read this if you want, but basically entropy, we've used S, and the change in entropy is delta S. This is a name that you've seen before with that Boltzmann curve. It basically shows the change in temperature and how it changes the particles that have the proper activation energy. Mathematically, you can find entropy by taking the K and then times the natural log of W, which basically is the arrangements that are possible in any given state. I wouldn't worry about this too much. This is just basically W is crazy. Like, more electrons you have, the more different places they could be. The W gets bigger and bigger and bigger, right? You have more states that things could be in. It's like a probability game. If we take a look, solid has the least amount of entropy, liquid more, and gas the most out of these 3 phases. As I said, vibrational and translational movement in the atoms is greater when heat is added. So something that is hotter has more entropy. And if you look at a perfect crystal at 0K, you have 0 entropy, no disorder. As you said, more ways of arranging the atoms and or electrons in larger molecules will have greater entropy. Just like delta H could be found with your standardized entrophies, delta H could be found with your standardized enthalpies. You can find entropy by taking the products minus the reactants, the summation of the entropy, and obviously this is per mole, minus the summation of the entropy for the reactants, just like delta H. So let's do some quick things. If entropy change is positive, that means that it's more random. which the universe tends to go towards. And if it's negative, it is less random. So if we take a look, let's just do this. We have carbon, and we're going to add to it oxygen, and we're going to get carbon monoxide. Does it become more random or less random? So there are two trains of thought here. It's only one thing now, right? So what else is happening? The solid would be the most uniform, right? The most organized. Yes, and it's going into a gas, which is making it less organized. Now the key here is you have solid here and gas here. Now the other key is here we only have how much gas? 1 mole. Remember, all moles of gas take up the same space at any given temperature and pressure. So here we have 2 moles of gas. Is 2 moles of gas more random than 1 mole of gas? Yes. So this is increasing entropy. Let's try this. H2O gas going to H2O liquid. Delta S positive or negative there? Yeah, that's less random. They're more organized. So delta S is negative. Let's try this. And I'm just trying to give you guys the examples of like each thing so that you can see what's happening each time. How about here? What do you pick out? What stats? This is gas, by the way. So it's delta S negative or positive. And what did you use to try to determine that?
Is it negative because it goes from 3 moles to 2 moles?
Good. Both of you got it right. Yep. We have 3 moles of gas here, which is pretty random. Here we only have 2 moles. So the particles, even though it got bigger, it's still negative there. Less random. Let's try 2 more. Magnesium oxide, solid, plus carbon dioxide, gas, plus, and that yields actually magnesium carbonate, solid. Pretty easy one here. Solid and gas going to just a solid. More organized. How about CO2 going to CO2? Both of these are in the gas phase. This one is at 300 Kelvin and this one is at 400 Kelvin. Yeah, right? More random, more energy, more random. The particles are moving faster. The change in entropy in the universe, as we said, is greater than 0 because things become more and more random. If we're looking at just a system, then if something is at equilibrium, it's a reversible process at equilibrium. Right at equilibrium, the change in entropy would be 0. Because you have something changing and becoming more random, and then you also have the reverse of that. Since it's a dynamic process, both things are occurring at the same time. Yes, yes? So whatever's becoming random, there's an equal amount of stuff becoming organized at equilibrium. So at equilibrium, delta S equals 0. All right, let's do one calculation of it. We have hydrogen and oxygen going to form H2O. All of these gases. So the entropy of H2 is 131 joules per mole Kelvin. Keep in mind that entropy is always in joules per mole Kelvin. For oxygen, it's 205 joules per mole Kelvin. And for water, it's 189 joules per mole Kelvin.
Mr. Jackson,
Yes,
how do you measure disorder?
right here. It's this formula right here.
Oh, okay.
Yeah, and as we said, we're not worried about it. Basically, Boltzmann said that the disorder is of a particular system is proportional to the number of different ways the molecules in the system could be arranged. So yeah, it's one of those things. You can dive into that hole if you want. I don't know how much fun you'll have though. But it's like a probability thing if you're interested in that. So if we take a look here, we know that the entropy change is equal to the summation of the final minus the summation of the initial. So here is our final. How many moles of that do we have? What's that? So this is 189 joules per mole Kelvin. We have how many moles of it?
2.
2. So we want to take 2 times 189. It gives us 378. Again, it is products minus reactants. So we have 2 moles of H2. So 2 times 131 is 262. And this is going to be the summation. And we have 205 because we only have 1 mole of this. So if we take a look, 378 minus 262 minus 205. Is this more or less random? Do we gain or lose entropy? Less. It's negative. The delta S is negative. And that makes sense from what we've said before, because how many moles do we have here? 3, and it's becoming 2. Yeah. The whole point of entropy is so that we could talk about Gibbs free energy, which is delta G. And I know that we've done a delta G problem in the past. I just told you that basically it's the same as delta H. Whenever you have the delta G's given to you, the Gibbs free energy of the reaction is equal to products summation minus summation of the reactant. And again, those standardized G tables, they'll give you that information like they did before. Gibbs free energy is basically the energy that is available to do work. It's the energy that you can't contain. It's just the energy that whenever a reaction occurs, it's given off. Like for example, like an engine warming up. You could use that to do something like people like on like we're going camping. Have you ever seen this? I don't know how popular this is anymore, but people would sit there and take like and wrap up something in foil and put it in their car and cook it as they're driving somewhere so that they would have a hot meal whenever they get out to camp. Right? It's a thing. You can look it up or whatnot, but yeah, it's kind of silly. If Gibbs free energy is the energy that can do the work, the S, that's the part that is basically just a dispersal of energy. It can't be used to do work. It's basically used to reorganize the matter. The delta S is just something that you can't use it for anything. So if we're taking a look for this, you can also find Gibbs free energy if you're given the standardized Gibbs free energy tables. Oh wow, I didn't realize how much lag I had here. Sorry about that. You can also, it's like a 15-second lag. You can also find delta G if you know the enthalpy, you know the temperature in Kelvin, and you know the entropy. Or if you have equilibrium, you can just take the negative R times T and times the natural log of the equilibrium constant. The one thing about this R is it is the 8.3, 8.31 R. It's not the normal 0.0821 R constant.
Is the T the temperature in Kelvin or something?
Yes, temperature in Kelvin. The delta S we just did is joules per mole Kelvin. So what's going to happen to kelvins? Cancel out. Delta H's though are not in usually joules, they're in what? Kilojoules, right? They're usually in kilojoules per mole. So that means that if you're using this formula to calculate delta G, you're going to need to make sure that your joules are changed to kilojoules because a lot of times delta G's are in kilojoules per mole. Questions there? I want the units of that. This R constant will be, that's what I thought, okay. This R constant will be given to you on there. This is the one you're used to when you're doing pressure formulas. This is the R constant when you're dealing with Gibbs free energy. And if you recall also when we dealt with work for, excuse me. So the units for that, 8.31 joules per mole Kelvin, which makes sense because we usually talk about K not having units or not worrying about the units, right? If we take the natural log of that, no biggie. And then since the T here is in Kelvin, that will give us our delta G in joules per mole, which then we could convert to kilojoules per mole. Cool. So when we talk about reactions, they can spontaneously occur. We call it, like you've heard of probably spontaneous combustion, and that occurs with chemicals, not with humans that we know of, right? You ever heard of that? Humans spontaneously just catching on fire. Yeah. With chemicals, this can happen. Something like this piece of paper, we may need to add energy in order to have that happen, right? But if a reaction is spontaneous, delta G is less than 0. That means delta G is negative. It's spontaneous. That means that the reaction moves toward the right in formation of products. If we're making products, then the ratio of Q over K, if we had a Q, would be less than 1 because that means that we're trying to get Q to K. Non-spontaneous is when delta G is positive, greater than 0. That's when we're shifting to make reactants. At equilibrium, delta G equals 0. So if we take a look, this little graph down here, this will help us out with figuring out whether or not a reaction would occur by knowing, well, delta H and delta S, because with knowing delta H and delta S, we can get delta G. So if we have a positive delta H and a positive delta S, well, let's look at this formula. I'm going to rewrite it because one, this is slow, and every movement I make, it seems to make it lag a little bit more. So if both of these are positive, what are the possible values for delta G we could get? Both of these are positive, possible values of delta G. Well, this is very big. And we
It could be
subtract,
positive or negative.
yeah, it can be positive or negative, right? Depending on the size of each of these. It could be positive or negative. As it says here, delta G could be positive or negative. If it was spontaneous, if the reaction was going to happen, delta G needs to be negative. How could we make delta G negative if both delta H and delta S are positive? Well, if T is big enough at a high enough temperature, then we would subtract enough to get this to be negative. We take a look, if we have a positive sign for delta H and a negative sign for the entropy or the disorder, there's nothing you can do because you're taking a positive and you're subtracting a negative, which will give you indefinitely a positive number. If both are negative, then it's going to happen. The reaction is going to occur because you have a negative minus. I'm sorry. If delta H is negative and delta S is positive, I did the math in my head already. I got ahead of myself. Then nothing can prevent this from happening because you have a negative minus a positive. And that's going to happen at all temperatures. Doesn't matter how cool or whatnot that is. And here, if a delta H is negative, you got a pretty good chance. That means it's exothermic, right? Delta H is negative. And if you're subtracting this, this could only occur at low temperatures because you don't want to subtract a big negative. So this would occur at low temperatures, if possible. Questions there? I wanted to give you guys good free energy. Oh, let's try this problem, the one all the way on the back. And also let's try this too. Let's say delta H equals 30 kilojoules per mole. Delta S equals 90.4 joules per mole Kelvin. And we've got bromine liquid going to bromine gas. So what does that make delta G if it's at equilibrium? If delta G is less than 1, we go in the forward reaction. If delta G is greater than 1, we go in the reverse reaction. What is it at equilibrium? Zero, right? So delta G at equilibrium equals 0. And what I would like for you to do is do this delta G equals delta H minus T delta S. I want you to find the boiling temperature then. By finding that T right there, if this is at equilibrium, you would be able to find the boiling point. Here's the entropy. Here's the delta H. So all you're doing is plugging that in. And here you're given some more information about bromine. And they want you to find out the G, and it apparently looks like it's not at equilibrium here. But they do give you the Kp. Oh, okay, that's a standardized. Cool. And I think that is it. Boom, 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 boom. That's all we're going to be able to get through today. Predict the effect. You guys should be able to do that one too. It's just dealing with Le Chatelier's, it looks like. Whew, questions. Oscar, did you get in here? Oscar? No. There's the link you were looking for last night when you're watching the recording. Any questions from those at home? Hopefully everybody's doing good. Again, I'd like to do a lab this week, but it doesn't look like we're doing it until Thursday or Friday. So I'll try to give a copy of that to you guys that come in so that you can read it before then. Have a great day.
So, Mr. Jackson, it says that the lab is due today. So, are we waiting until people do it, or are we turning it in today?
I'm sorry, I don't understand.